we already know that conservation of energy is a pretty big deal, and we've got a new energy type now, so it makes sense that we would expect to see some problems with conservation of energy where rotational kinetic energy plays a part. So one type of problem that we'll see with this is for an object rolling down a hill. So they might give you a variety of information here, but in this one we're given the mass of the sphere, the fact that it's a solid sphere, which lets us figure out the rotational inertia from the table in your book. It rolls from rest, and we're looking for how fast the speed it is, what the speed of this thing is, so that'd be the linear speed rather than the angular speed if they don't say otherwise, when it reaches the bottom if it starts from rest. So here's sort of a general picture of what's going on in terms of energy. We start with nothing but gravitational potential energy, and at the end all that gravitational potential energy is changed into either translational or rotational kinetic energy. So we can write an equation based on that then. Whatever gravitational potential energy we start with, so that's our initial, has to be equal to the final kinetic energy plus the final rotational kinetic energy. And we can write expressions for each one of these things then. So mgh initial, that'd be the starting position, the starting gravitational potential energy. And then kinetic energy is 1/2 mv squared. It's final velocity. And rotational kinetic energy, that's 1/2 I omega final squared. Now in this equation I see, got some things I don't know values for. Let's see, I know my mass, gravity's 9.8 meters per second squared, initial height is 1.0 meters, so I'm good there. Mass I know, final velocity I don't know, but that's what I'm looking for, so I wouldn't expect to know that here. But then this one's trouble. I've got I, the rotational inertia, I don't know, and I've got omega final, don't know that one either. So let's see what we can do with this. Well, it's a solid sphere, so from my textbook then, I can look up the equation for the I for a solid sphere and find that that's 2/5 mr squared. So I can plug that into my equation. And what about this omega? Well, it says that it's a ball rolling without slipping. And what that means is that every time the ball goes a distance that's equal to the circumference of the ball, that ball has traveled one time around, or it's traveled through 2 pi radians for its angular position change. So when we had that state, we could say that our speed, our linear speed, is equal to omega times r, the angular speed times the radius. So we can actually rewrite that as omega equals v over r. I still don't know v, but that's okay. That's the variable I'm looking for at the end here. So let's plug these new equations in. We get mghi 1/2 mv final squared plus 1/2, and then I was equal to 2/5 mr squared, and then omega is going to be v final over r, and then that gets squared also. Okay, well this is looking better. It's still kind of a tricky equation, but at least I've got all variables that I know, or the one variable that I'm looking to solve for here. Let's see. Got kind of a mess on the right side there. Let's go ahead and simplify that as much as we can. So I keep all of this part the same. Alright, and then I've got the 1/2 times the 2/5, so that gives me just 1/5. And then m. And then that v over r squared, that's going to be v squared over r squared. So then I'll have r squared on top and r squared on bottom. So that'll cancel out altogether, and I'm going to end up with just vf squared. No, and then I see 1/2 m vf squared and 1/5 m vf squared. Those are common terms. I can combine those. While I'm at it, I see that every term has an m in it, so let's divide every term by m. And so we get g hi, so I've divided out the m, is equal to, see, I want to add 1/2 vf squared and 1/5 vf squared, so we better find a common denominator here. Or, you know what, let's just use a decimal. So this is 0.5 vf squared, and 1/5, that's 0.2 vf squared. So we end up with 0.7 vf squared. So GHI equals 0.7 vf squared. Hey, that's an equation we can solve, so let's go ahead and plug in our known values on this one. So I've got 9.8 meters per second squared. Got my initial height of 1.0 meters. It's equal to 0.7 times vf squared. And this is interesting. The mass actually doesn't matter on this one. The mass of the ball doesn't matter. What does matter is, well, this 1/5 term that we get happened because we had 1/2 times 2/5. So the fact that it's a solid sphere and not, say, a cylinder or a hollow sphere, that mattered. But the mass of the ball actually doesn't matter in this problem. Alright, so we'll do our 9.8 times 1. It's just 9.8 still. And then we'll divide that 9.8 by 0.7 and square root both sides. And we end up with 3.74 meters per second is equal to our final velocity. So that's fast enough that the combination of kinetic energy due to moving place to place and kinetic energy due to rotation, those two added together equal the gravitational potential energy that we started with, and energy is conserved. Thanks very much for watching, folks. If you found this useful, please like it so other people can find it as well. And if you think you'll find future videos useful, go ahead and follow the channel, subscribe to the channel. Thanks again.